Exponential random variables have a property called memorylessness, which means that our opinion about how much longer we're going to wait for an occurrence does not depend on how long we've waited so far. So first of all, let's look at this problem for a general random variable. So for any continuous random variable, we have that the probability that x is greater than or equal to b, given that x is greater than or equal to a, is just probability that x is greater than or equal to b over probability x is greater than or equal to a. So the reason is, let's let this be the density function. So I'm thinking of a as being a number which is less than b. So if we know that x is greater than or equal to a, what's the probability that x is greater than or equal to b given that x is greater than or equal to a? So the probability that x is greater than or equal to b given that x is greater than or equal to a equals the probability that x is greater than or equal to b and x is greater than or equal to a divided by the probability that x is greater than or equal to a. But if b is greater than a, then the probability that x is greater than or equal to b and greater than or equal to a is just the probability that it's greater than or equal to b. So it's just probability that x is greater than or equal to b on top over probability x is greater than or equal to a on the bottom. And we can see that given that we're greater than or equal to a, the probability that we're greater than or equal to b is this area divided by the whole area which is shaded. Probability that x is greater than or equal to a. Now this formula becomes even simpler in the case that x is an exponential random variable. So x distributed as an exponential random variable with parameter lambda means that x is the waiting time between occurrences of a Poisson random variable with expected frequency of lambda occurrences per unit time. That means the expected value of x is 1 over lambda. So if we expect 3 occurrences per unit time, that means we expect to wait 1/3 of a time unit to get the occurrence. And the probability that x is greater than or equal to k is e to the negative lambda k. Alright, so the simple form for this formula is that, so if we have x exponentially distributed with parameter lambda, we have that the probability of x being greater than or equal to b given that it's greater than or equal to A, equals the probability that x is greater than or equal to b minus a. Again, I'm thinking of a as a number which is less than b. So the reason that we don't even need a fraction in this case is that this is the probability that x is greater than or equal to b over the probability that x is greater than or equal to a, like it is for all random variables, all continuous random variables, which is e to the negative lambda b over e to the negative lambda a, which is e to the negative lambda b minus a, which is the probability that x is greater than or equal to b minus a. So this means that after waiting a time units, or let's say waiting time a, for an occurrence which hasn't happened yet, we believe that the probability of waiting b minus a more time units, or time b minus a in addition, equals the probability of waiting time b minus a in the first place. So how long we've waited so far does not influence our opinion about how much longer we're going to wait for the occurrence. And I'm not sure how much that happens in real life, that no matter how long we wait, that has no influence on our opinion about how much longer we'll wait. So this is why the exponential distribution with probability density function lambda e to the minus lambda x is famous for being, first of all, easy to integrate, second of all, unrealistic. So, just to do one example, so for example, suppose we have a car battery and we model our opinion about its lifespan with an exponential random variable. Let's say we expect the battery to last 10,000 miles. The question is, how confident are we that it will last at least 5,000 miles. All right, to save ourselves from writing a lot of zeros, let's let x be the actual lifetime of the battery in thousands of miles. So the expected value of x is 10. And x is an exponential random variable with mean 1/10. So 1/10 is lambda. Which is the frequency of battery failure per time unit, which in our case is 1,000 miles. So we expect 1/10 of a car battery to die every 1,000 miles, or we expect the battery to last 10,000 miles. So that means that the probability that x is greater than or equal to 5 is e to the minus 1/10 lambda times 5, which is e to the minus 1/2, which is 1 over square root of e, which is 0.607. So that's the probability with which we believe that the car battery will last at least 5,000 miles. Then after one 5,000 mile trip, I guess our opinion about the battery lasting another 5,000 miles is just the same as it was before. And then after two 5,000 mile trips, our opinion about the battery lasting another 5,000 miles is the same as it was before. Which I think is pretty silly. But the computations were really easy because that's just an exponential function. The end.